Okay, I guess recording has started. Now we have 9 people out of 19 registered. So let's see, where's my presentation? Okay, so today we will talk about causal inference. I'm not really an expert in causal inference, so that's why I will touch on a few things which I have used previously in my practice. And we will talk about propensity scores, inverse probability weighting, and potential outcomes. By the way, do you hear me well? Can please someone confirm?
Yep, fine.
Okay, good. Yeah, thank you. So first, a few slides about our CTSI BERT, Biostatistics, Epidemiology, and Research Design, CTSI function. Director is Dr. Huang from UWM, and we provide statistical support through several locations: UWM, Biostatistics, and CAPS. So how you can get biostatistical support? You can apply for mini grants, and typically these mini grants are awarded, and principal investigator receives 4 to 6 hours of statistical support. Mostly these mini grants are for design purposes. So we help investigators to design their studies, so we can review and confirm the data analysis plans, perform power calculations. We can even perform some short preliminary data analysis specifically for designing studies. For example, if you're writing a grant proposal, we can, do some initial preliminary analysis which are needed for power calculations. Okay, should I scroll down? So, and our biostatistical consulting services, which is part of Division of Biostatistics, Institute for Health and Equity. So we provide some more services beyond what is supported by mini grants. So in this case, we have listed all the same services over here, plus additional services, like more comprehensive data analysis, working with large databases, etc. Our services are not free. So, and for MCW personnel, PhD hour from Biostatistical Consulting Services are $165, and a data analyst is $100 per hour. And we do have integration contracts with a few departments within the MCW and some divisions within the MCW. And here we have listed them. Here we listed them here. So if you belong to these departments or divisions, you can receive biostatistical assistance for free from our division of biostatistics. Content of today's presentation. We will talk about differences between observational studies and randomized control trials. We will discuss differences between averaged treatment effect and averaged causal effect, and how averaged causal effect can be estimated. In causal inference, I cover 2 approaches. One is based on propensity scores, which propensity scores can be used to design weights, so-called inverse probability weighting approach. And I will show you an example in R, and I'll show you all R code. It's like 3 slides or so, where I show the benefit of propensity score, how on an artificial example. Second approach.
Sergey? Oh,
yes.
Sorry. Are we supposed to be seeing any slides right now?
Oh,
I
you don't see my slides?
No.
Okay, I'm really sorry. Oh my God.
No worries.
Okay, I guess what I've done wrong, I did not share my screen. Okay. Do you see my screen now?
Yeah, I see the RStudio.
You see RStudio. Okay. Let me just move presentation over here. Okay. OMG. Okay.
There, it looks good.
Okay. So let me briefly go quickly from the beginning because it's then it's visual, it's kind of simpler to see. Okay. Causal inference, as I mentioned, we'll be talking about propensity scores, inverse probability weighting, like bigger, and potential outcomes. CTSI bird function, so I talked about this one, provide statistical support through 3 different locations. Zilber School of Public Health, UWM, Division of Biostatistics through Biostatistics Consulting Services, and Center for Advanced Population Science through CAPS. As I mentioned, mini grants provide support for study design mostly, plus some preliminary data analysis, mostly done for power calculation purposes. Beyond what is covered in these mini grants, so we can provide additional services, but these are for fee services. And here we have list of topics which you have list of topics which list of services which you provide beyond what is covered by mini grants. And I mentioned that our fee for service is like $165 per hour for a PhD, and for a data analyst it's $100 per hour. And we do have integration contracts with a few departments: surgery, orthopedic surgery, physical medicine rehabilitation, pharmacy, product pharmacy, and divisions of pediatric emergency and hematology oncology. So, content of today's presentation. Today, we will talk about differences between observational studies and randomized experiments. We will talk about differences between average treatment effect and average causal effect. And in observational studies, we are typically interested in estimating average causal effect. And we will consider 2 different approaches how this can be done. One approach uses propensity scores to calculate inverse probability weights. And I will show you an example in R. So it will be like 3 slides, how propensity scores can be used and what are the benefits of using propensity scores to calculate for weights calculation and proceeding with weighted analysis. Potential outcomes and multiple imputations, that's another approach, how you can estimate causal effects in observational studies. And we will show an illustrative example, how to evaluate vaccine effectiveness using observational data. So it's still unpublished manuscript, so we try to publish it. We submitted different places, still we're not successful yet, but it seems to me it's a good illustrative example to show the power of causal inference in observational studies. Then I would spare just 1 slide to talk about more generally about causal relationships and 1 slide summary. My presentation total about 30 slides. So for observational studies and randomized experiments, so contrasting these 2, I will be using the slides from Judy Pearl, and set of slides are, I will be using a few slides based on this paper, which is freely available online. So if you want to see more details on causal inference, you can easily go and read this paper. Traditional versus causal inference. So I took a few, very interesting sentences from her publication and copy and pasted them here. The aim of standard statistical analysis, typically regression analysis, estimation, hypothesis testing, but these are based on the distribution of the data. So we would assume that all information is available in the distribution of our data. And when you run a regression analysis, you rely on this distribution. And these statistical methods were developed, all of these standard statistical methods were developed mostly for experimental conditions, which remain static, remains the same. In causal inference, it's like in second second item here. In causal inference, we go in beyond these static conditions, and we can also evaluate a few what-if scenarios, right? So what happens if? So in this case, we are changing this static situation to something else. And we will have a few examples to that. So what would happen if, for example, we have interventions to the whole population? Causal assumptions. So when we're talking about just joint distribution between symptoms and diseases, they do not tell us much about curing, but curing symptoms will cure a disease. So we don't really know that. And more generally, if we're looking at a joint distribution, without any additional external information, we don't really know what affects what. So, for example, if we have like two variables like t and y, and we know their joint distribution, we don't know whether it's t affects on y or y affects on t. We don't know this causal association, causal relationship. So that's why, clinical trials are important, because in clinical trials, you can set experimental conditions. So, and by setting experimental conditions, later you observe your outcomes. So in this case, you can, infer causal relationship between the experimental settings and the outcome. But in observational data, you typically cannot do it unless you have some additional information, some external information, external to the data. So the laws of probability theory do not dictate how one property of a distribution ought to change, then another property is modified. So this is what we don't know. This information must be provided by causal assumptions, So, and that's why I put here, like, instead of T, I put like a treatment and the outcome. For example, if person is vaccinated, what do we expect? Do we expect a reduction in chances of COVID? Maybe yes, maybe no, if you look at observational data. That's why a clinical trial was performed, randomized controlled experiment, where we could infer the effect of vaccination on decreasing COVID chances. Causal assumptions. So you heard this phrase, correlation does not imply causation. And in Judy Pearl's paper, she translates this into one cannot substantiate causal claims from associations alone, even at the population level. Behind every causal conclusion, there must exist causal assumption, which is not testable on observational data. Now we will talk about averaged treatment versus averaged causal effect. If we perform in a randomized experiments, right? So clinical trial, we have randomization between two groups. So what we're typically interested in estimating average treatment effect, right? So for example, here we see T is equal to either 1 or T equal to 0. T, it's a treatment, right? So it's either a control group if T equal to 0, or it's an intervention group. So, but in this case, by the virtue of randomization, so we can assign, like 50% of participants in one group, 50% in another group. And then we can unbiasedly estimate, without any bias, average treatment effect, which is defined in this manner. So Y is a study outcome. For example, it's like probability, not probability, it's an event whether whether person get COVID or not, suppose in 2 months post-vaccination, right? So, and if we have a randomized study, in this case, we can estimate this effect ATE without any bias. But at the same time, even in this experiment, you are not assigning a person to both conditions at the same time. So that's why there is still person effect, right? In observational studies, we are interested in so-called averaged causal effect. Averaged causal effect, which is defined in this manner. Expectation of Y, so it will be our outcome, again, COVID versus no COVID, and minus expectation of Y, again, COVID versus no COVID, but previous expectation was taken conditional on T equal to 1, but here we have really interesting operator do. They will talk about this operator a little bit more, but essentially we are talking about a hypothetical scenario where everyone in your population is actually assigned to the treatment, assigned to a vaccine. Suppose we have like 100 million people, eligible for vaccine, and all 100 million actually receive this vaccine in our population, right? And suppose another scenario, another hypothetical scenario, that everyone in our population do not receive a vaccine, all receive a placebo, right? So, and that would be difference between responses between these two hypothetical scenarios will be our averaged causal effect, because this averaged causal effect does not really exist in real life, right? Because in real life, some people would receive vaccines, some do not, and importantly, these groups are very different. Okay. So, and that's why, if you look at observational study, if you would just want to compare those who got vaccines and those who did not get vaccines, these are different groups. Those who got vaccines are typically older, and those who refused vaccination are typically younger. So what does it mean? It means, well, outcomes potentially different. For example, if you're looking at the outcome, not say, we are not looking at COVID versus no COVID, but we're looking at mortality, right? So for older people, mortality is definitely higher. So that's why there is a confounding with some variables. So it's why there are different biases. So, and if we ignore observational nature of the experiment and just want to compare like two sample means between two groups, vaccinated versus unvaccinated, we are in trouble because there are plenty of different biases. And that's why estimation of causal effect is tricky, because we have to account for these biases. Oh, I already been here. Next part. Yes, so yeah, and I already talked about this topic a little bit, because in observational studies, patients do select whether to proceed with treatment or do not proceed with treatment. And there are many different factors, affecting this decision. In observational studies, ATE, average treatment effect. When I say treatment effect, we typically think about a randomized clinical trial. Does not describe only treatment effect in observational studies. If you would just consider difference between sample means, right? But this effect also encapsulates all the baggage which comes with it. It's like differences in, belief in conspiracy theories, or difference in ages, or eligibility, or availability of a drug, or whatever. Everything is incorporated into this difference which we actually observe. If you would just try to apply difference between sample means, this is what we typically have in randomized clinical trials. Yeah, and I already talked about this. For example, how one would explain averaged causal effect of mRNA vaccine on mortality rate if older patients with higher comorbidity levels are more likely to proceed with vaccination. Let's look at this example. So, and in this case, I specifically go from more general like T treatment and Y outcome. I specifically said, in this example, we have 6 people who are vaccinated and, 6 people who are not vaccinated. And I put some ages over here. So, and we do observe some outcomes. So this is what our data look like, right? So our average treatment effect would be expectation, like probability to get COVID, say 2 months post-vaccination in vaccinated group minus unvaccinated. So, and this quantity, average treatment effect, is correctly estimated without any bias if we have randomization, okay? Because randomly assigned, so in this case, we do have estimate average treatment effect. Okay, so I'm going again. So if we do not have randomization, we have bias. And here I posed a few questions. What if patients can choose vaccination? What if older patients more likely to choose vaccination than younger patients? What if the outcome also dependent on age? And it might depend on age, the outcome. If vaccination depends on age, regular sample means in vaccination, no vaccination groups are biased estimators of these two expectations, which lead to overall bias in the estimation of average treatment effect. So what Julia Pearl suggested is that we can consider a hypothetical scenario, and I have already touched about this, when all patients in the population receive a treatment. I'm going back to my example, all 100 million of eligible receive vaccination, right? That's one scenario. Hypothetical, counterfactual scenario, never happens in real life, important. Or alternatively, nobody receives vaccination. So this is what operator do describes. But I have also seen that this do operator in some cases is used to describe interventions, okay? So like randomized interventions. So this creates a hypothetical scenario, as I described. Okay. Yes, I already talked about these unrealistic settings. We go down. Consider an objective to estimate average causal effect. So, and this is how we define this causal effect, because we consider this hypothetical scenarios that everyone gets treatment and no one gets treatment. So, yeah, and I already talked about this, that, you know, real outcomes is not available for everyone. And another problem is that we never jointly observe, you know, treatment or under treatment and no treatment scenarios. So the two possibilities how we can analyze this data in observational studies. One is called propensity score, and propensity score can be used in different ways. And one possibility to use propensity score is to calculate weights for each individual in our data set. This approach is called inverse probability weighting, IPW. That's one possibility. And another possibility is that researchers can proceed with imputations of potential outcomes. And we will talk about these two approaches down below. Okay. Propensity score. What propensity score is? Propensity score is just a probability that this person receives a treatment with given some specific person-specific characteristics. And in our example, we have assumed that our baseline characteristics of a person is just single one, that will be age. So in this case, age is associated with whether a person receives vaccination or do not receive a vaccination. So when propensity score model, it will be just a conditional probability of vaccination for given age, We typically don't know this probability. So what do? We need to estimate this conditional probability. And what is typically used to estimate this conditional probability is a logistic regression model. So that's why it's easy to implement. How these propensity scores are used for weights calculation. So when we ran a logistic regression model, when we fitted a logistic regression model on our data set, so for each individual, we can calculate probability of being vaccinated. So we know actual status, whether this person was vaccinated or was not vaccinated, right? So we know the status. But when we fit our logistic regression model on the whole data set, we can calculate probability of being vaccinated for each individual. And then these probabilities are used to calculate weights. And weights are calculated in the following manner. So that would be inverse probability to receive a treatment that this person actually received. Okay, so this means that for those individuals in our data set who actually received the vaccination, weights would be 1 over probability of vaccination. And those who did not receive vaccination, weights are different. Weights would be 1 over probability that this person did not receive vaccination. Okay. So that's important. I did not specify it here, but yeah, keep it in mind. So in this case, that will be probability. That will be for subgroup of individuals who are vaccinated. That's a first line. And second line, that will be for those who are not vaccinated. Okay. So we have 2 different groups of weights. And here we have our example, which illustrates how inverse probability and propensity scores do work. So first, I have created a simple model. So I created like artificial sample of 5,000 people, right? And I have generated ages roughly between 0 to 100, right? Just randomly. And probability of being vaccinated depends on age. So I do have some formula, how it depends on age. Then our outcome, suppose it's like mortality, maybe like 2 months post-vaccination, right? And I also have a formula, how mortality depends on 2 factors, on age and on vaccination status. So that's important because age and vaccination status, they both affect our outcome. So what is happening here is that here we see the effect of vaccination, which is equal to negative 0.2 on logit scale. And if you exponentiate this value, you would get odds ratio, right, which we are interested in. This odds ratio would describe the effect of vaccination on mortality, on 2 months mortality. So what is happening in our data set? Since, age is associated with vaccination status. So that's why when we compare average ages between those who are vaccinated and those who are not vaccinated, we see a very interesting picture, because mean age across those who are vaccinated is 53 years of age, but those who were not is 44. Well, 9 years difference, 9 years difference. And you remember, older people are more likely to die, right? So that's why if you would start running our analysis ignoring this confounding variable, we are potentially in trouble. So, but overall age in this group is like 49.7 years of age. So, as I mentioned, that if we run our analysis and we are ignoring the effect of age as a confounding variable, we are in trouble. And if I run a logistic regression, because logistic regression can be used to evaluate the effect of vaccination on mortality. And my regression coefficient is negative 0.10. So if you exponentiate it, you get odds ratio. But this negative 0.10 p-value is 17%. So there is no significant effect of vaccination, right, on the outcome. And you remember we have like 5,000 people in our data set because we did not account for age. So since we know our model, so potentially, we can include the effect of age and we get the correct number. So that's a nice part about regression analysis, because regression analysis do allow you to control for the effect of confounding variables, and you are estimating what you need to estimate, okay? But you need to know what your model is, and it is really easy to misspecify your model. But again, regression analysis is just one possibility. How this propensity score approach works. In propensity score, so as I mentioned to you before, we feed a logistic regression model. So, and this is the R code in second line, how we can feed a logistic regression model. So we try to predict vaccination status on the basis of age. So this second line, and we save our result in object fit. Then we use this object to calculate predicted probabilities. So for each individual in our data set, for all 5,000 of them, we calculate probability that this individual gets a vaccination, gets a vaccine. Then in next line, weights. So we calculate our weights. So weights are calculated using inverse probability weighting approach. So for those who are vaccinated, it will be 1 over probability of being vaccinated. And for those who are not vaccinated, it's like second part. That will be probability, 1 over probability of not being vaccinated. We calculated these weights. And you know what? When we proceed from here, we proceed with weighted analysis. So we calculated weights, and the weights are in one group, in vaccinated group, mean weighted age is 49.7. In those group who are not vaccinated, weighted age is also 49.7. So what this weighting did is that we equalized our vaccination groups in terms of their baseline characteristics. In this example, we equalize them in terms of age, but to equalize them, we need to apply weighting. And this is what inverse probability weighting does. So in this case, we are balancing out our covariates. And this is what we typically see in randomized experiments. Because if you have randomized experiments, right? So it's like flip a coin randomization. So in this case, assignment to a group is completely independent of anything. So that's a nice feature of randomized experiments. That's why randomized control trials are so important, because by the virtue of randomization, our groups, intervention and placebo groups, they are approximately the same in terms of their baseline characteristics. But this is what we do it. But here we do it using weighting, okay, inverse probability weighting. Sometimes this setting is called pseudo experiment, because we are not really performing a true experiment, right? But by the weighting, so we approximate the scenario of a randomized clinical trial. Okay. So, and then in this case, if we run our analysis, if you would just apply the same analysis, which was not correct initially, let me go up, you see, it's like when we run our logistic regression, where our vaccination is the only predictor in our model. So we get a biased estimate, negative 10, and p-value was not significant. But now, if you use weighted analysis, so you see in my logistic regression, which is fitted in the end of this slide, so we applied weights. So it's exactly the same logistic regression where we use vaccination status as the only predictor, but we also use weights, right? So, and you see our vaccination, regression coefficient with vaccination is negative 0.19. It's really, really close to our true value of negative 0.2 from our initial statistical model. And p-value is highly significant, okay? So yeah, that's the nice part about inverse probability weighting. And this is one possibility how propensity scores can be used to equalize populations. Some people also use propensity scores in a different manner. You can use propensity scores to perform matching. So for example, for each case in your study, for example, case, it will be a vaccinated person, right? You select a control with similar propensity. This is so-called propensity score matching. It's a useful approach, but it's a different approach, and propensity score matching on propensity score estimates a different quantity. Because, for example, suppose we are talking about a rare disease, right? And some individuals get some disease, right? But this group of patients is distinctly different from overall population of controls. So, and then you do matching on propensity score, you essentially select controls from similar at-risk population. So that's why it's kind of difficult to extrapolate your finding. It is still possible, but you know, when you just consider like matched case control sample, matched on propensity scores, from this sample, you're estimating a slightly different effect. So you're estimating effect of this disease on whatever your outcome is, but for at-risk population. Okay. So yeah, so this is one of the possibilities how you can use propensity scores for estimating averaged causal effect. Potential outcomes. That's another approach how we can estimate averaged causal effect. So just to remind you, randomized clinical trial, we are estimating average treatment effect. In observational studies, we are interested in estimating average causal effect. So, and we already had this picture, but in addition to first three columns where we have vaccination, age, and COVID, right, as an outcome, we added two extra columns. So in this case, that will be columns of potential outcomes. So in this case, we have infection if person was treated, and infection if person was a control, treated with vaccination and not treated with a vaccination, right? So what is happening? In this case, we assume for each individual, there are two outcomes, but only one is actually observable. For example, in vaccination group, among those people who are not vaccinated, I mean, first 6 patients, vaccination status is 0. So what we observe I mislabeled it. Oh, yes, this is correct. Okay, so we observe our outcome only under the condition when there was no vaccination. But another outcome is only potential, it's virtual, it's non-existent in real life, right? So, but we assume it exists in some counterfactual world. So that's why it's called a potential outcome. So this potential outcome, where I put these question marks, is not observable. On the other hand, if you're looking at second part of the data, for those people who are actually vaccinated, so we also have two outcomes for each individual, but we do observe outcome where treatment was applied to this individual. Okay, so outcome under treatment is available, but outcome under the control condition is not available, is not observable. So these are the potential outcomes. And you know, when you look at this data, what do you see? You see a missing data problem. Okay, so and the most and how do we deal with missing data problem? We typically use like multiple imputation. It's one of the possibilities how missing data can be treated. One of the popular approaches. Yeah, and here we show a few slides. I mean, a few imputations, a few basic steps for multiple imputation model. So what do? So step 1, we develop an imputation model predicting potential outcomes. So, so we take our data, right, and we try to predict what might be happening in one situation or another situation. So step 2, we developed our imputation model, and then we try to make predictions what might be happening. So, and during imputations, because imputation is not just a single imputation, because there are different approaches for imputation. So, and in single imputation, you just plug in single number, just one data set, you know, with imputed values. But in multiple imputation, you impute multiple, you generate multiple data sets, and every time you have a slightly different combination of imputed values, because you impute not just a single number, but from a random variable, from a random distribution, from a distribution of random variable. So since our potential outcome is a binary variable, yes, no, so that's why it's so-called Bernoulli random variable, and you have a probability of success, right? So, and you just generate data with this probability of success or failure. Infection, it will be like a failure, right? So it will be you're generating possible values for this missing outcome. So then you generated this multiple data sets, like say M different data sets. Then for each data set, you calculate what your treatment effect is, right? So in this case, it will be just difference between two columns, average difference between two columns for each data set. And then you need to combine the results from multiple different analyses from each imputed data set using formulas published, for example, in Little and Rubin book, Statistical Analysis with Missing Data. Because you just need to be careful how you combine results from all of these analyses all together. Because you got to be careful about variance, because variance would be different. And here I will show you an example how potential outcomes can be used, this framework on potential outcomes and multiple imputations, how it can be used to estimate averaged causal effect of vaccination on the outcome. But before that, I will just have a snapshot from a publication from Pollock et al. In 2020, where they described that this Pfizer vaccine was efficacious, and they have shown that out of 21,000 patients who got this vaccine, so during 2 months, I think it was on average like 2 months period, follow-up period, only 8 actually received the vaccine. Maybe it's like 7 days post-vaccination. This is when the observation period started. And in the control group, they had 162 COVID cases, so many more. So, and that was the reason how they calculated vaccine efficiency. They estimated vaccine efficiency to be 95%. And vaccine efficiency is defined like 100 times 1 minus incidence rate ratio, IRR, which is a typical quantity used in epidemiology. But for simplicity, in our case, since we have the same follow-up period for 2 groups, that will be just ratio of 2 risks, risk of infection in one group divided by risk of infection in another group. So that's why IRR is equal to 5%, so which leads to efficiency of 95%, okay? Now, but that was a clinical trial with 43,000 people, right? Extremely expensive. So what we did, it's a group of researchers, including myself, Dr. A from our division, and Dr. Moyer from our Institute for Health and Equity. So in observational studies, IRR, we can estimate IRR, but the problem is we do not have randomization between two groups. So, and before each study, we need to pose a question we would like to address. And here I listed the question which was not yet addressed, in this previous study, when, vaccine efficiency was shown in the clinical trial. So we want to investigate vaccine efficiency and how it changes over time, say 6 months, okay? Because we had some follow-up already. And this research question was not addressed in this clinical trial, which was published before. So, and we focus on post-vaccination causal effect, and this is what we said. So you see, numerator would stay exactly the same because I'm interested specifically in group of Pfizer vaccinated patients, okay? But in the denominator, we do have this counterfactual scenario because we would like to evaluate what would happen with these patients who actually received vaccination. What would happen if they would not receive vaccination? So that's why numerator is an observable quantity, but denominator is a counterfactual quantity. So, and we took a data set, it's like more than 1/3 COVID test results from almost 200,000 patients from our frauded hospital. And we used clinical research warehouse database. We extracted multiple tables like demographic table, vitals, diagnostics, procedures, diagnostic results, immunizations, a lot of tables, a lot of data. And initially we processed this data using Jupyter notebooks available through CTRI. And then we used SQL and R for initial preprocessing. Then we downloaded this data set on our computers and analyzed the data. So when we look at this data, all of these, 200,000 patients. So what we see, and here we have like in separate columns. One column, it will be Pfizer vaccine, those who are vaccinated. You see average age is 55. Those who got Moderna, 64 years of age. Those who got COVID without any vaccines, average age was 42. And those who did not, who were not vaccinated, and before, we looked at PCR tests before they got COVID. So average age was like 45. And, when we have this COVID column, so that will be after they got COVID, because, each participant had like multiple different tests. So that's why we could split tests into different groups. And other, it refers to other vaccines like Johnson & Johnson and other. So I don't know, it seems to me it's only supposed to be 3 vaccines which are approved, but we also had some other vaccines. I don't know where these come from, but these just single digits mostly. The bottom line is that these groups are different. These groups are different and they have like many different characteristics. So what we've done, we have used this multiple imputation approach. So, and we imputed possible plausible values for the scenarios where patients who received vaccination would not receive vaccination. So, and we got 2 curves in this case. So if you look at left panel, so in this case, red line shows on x-axis shows time post-vaccination. So, and in this case, we could estimate probability to get COVID. So, and for those who are vaccinated, that will be a black line. So you see black line quickly goes down, and we see that, probability to get COVID, like during first 2 months, right? And maybe like between 1 to 3 months is extremely small. And after it starts climbing up. Okay. If you look at group of those who did not, if you would consider a hypothetical scenario that the same individuals who got vaccines would not get a vaccine, right? So we could also predict a probability how likely you will get COVID, for this hypothetical scenario. So, and this is where we got our red curve. So you see, this red curve is also kind of mimics our previous curve, because there are plenty different confounding variables here. So, and then we consider ratio of these 2 curves and calculate a quantity which is mimicking vaccine efficiency. But, we cannot estimate vaccine efficiency because we do not have a clinical trial. Vaccine efficiency is like an average treatment effect, but we estimated average causal effect. Okay, so it's a similar quantity, but estimated on observational studies, because we involve like a hypothetical scenario over here. So, and this is what we see. We call it vaccine effectiveness. Okay, estimated vaccine efficiency. So we're going up close to 90%, and you see what Pfizer's clinical trial showed, 95%. That 2 months. But and it's about 2 months value, right? This is where we had 90% efficacy. And then they start going down to about 50% by 6 months or so. And after we did not have much data. So if you look at another vaccine, Moderna, we see similar picture. We see, but we see a stronger effect of Moderna vaccine, and we actually had like more volume of their vaccine, right? So like 30 milligrams as compared to like 100 Moderna, Pfizer versus Moderna. So the effect is stronger and it stays longer, but after it also goes down. And we had these findings in November 2021, and we were trying to publish this paper, still unsuccessful. But what we see later, some other papers showed up, they shown the same picture. So in March 2022, December 2021, this Qatar study showed, that vaccine efficiency goes up, but after it winds down, goes up and goes down. Okay. So this example shows, power of this potential outcome framework. which allow you to evaluate vaccine effectiveness, on the basis of observational studies. So we consider just two possibilities how averaged causal effects can be estimated: propensity scores and inverse probability weighting, and potential outcomes and multiple imputations. But more generally, researchers who work in causal inference, they build causal diagrams, and in causal diagrams they have all kinds of relationships. And here I post I have actually copied and pasted this slide from this WordPress.com website, and this blue part, this is what I copy pasted, and I have added also instrumental variable. So we're interested mostly in how exposure affects our outcome. So this is a causal relationship of our interest. But in real life settings, so we can see confounders. So the variables which affect both and exposure and the outcome, like age. This is what we saw in our example. There are some mediating variables, because it is possible that, for example, vaccination affects behaviors, right? And people feel protected, after vaccination, and they more likely to show up, in public, more likely to be exposed to virus, and maybe more likely to be infected. Another possibility, it's like moderator. So moderators, this is from a statistical perspective, we typically call moderators interactions. Okay, sometimes people say effect modifiers. So in this case, the effect of our treatment variable or the effect of exposure can be, modified by some other factors, by moderators. And another variable here we see is a covariate. Covariate, that will be an independent predictor. So covariate affects the outcome, but is not directly related to these other things. Okay. And a short summary: observational studies can provide valuable information which is difficult to obtain from randomized clinical trials. Certainly, observational studies not the same as randomized clinical trials, but they still can be very, very useful and very cheap. Estimation of averaged causal effects can be done using imputation of potential outcomes or inverse probability weighting. Maybe there are some other approaches. I just discussed only these two in my presentation. The question appears, which one is better? Well, I don't know, but you see, each of these approaches to estimate the same averaged causal effect have some limitations. For example, when they consider multiple imputations, they depend on an imputation model. And it's really difficult to mass specify this imputation model. But nice part is that, set of covariates stays the same. So in this case, if you want to estimate treatment effect under given set of covariates stays the same. Then we're talking about propensity score. Propensity score is also dependent on the model, because we used logistic regression model to evaluate propensity scores. And it can also be misspecified. It can be, you can incorrectly estimate, these propensity scores. And the distribution of the covariates, so it's balanced only in terms of like marginal this propensity score. But on average, you still can see some differences, because if there are multiple variables which are contributing to the propensity score, it is still possible that propensity scores are similar and distributions of propensity scores are similar between groups, but distributions of covariates are still a little bit imbalanced. Okay, and that's all what I had for you today. Questions? We still have a couple minutes.
I have a question, Sergey. Regarding your example earlier, where you used propensity scores to sort of like equate groups of interest on covariates, what would be the reason for doing that as opposed to just adding your covariates into the model as covariates?
You typically, because these are both are reasonable approaches. Okay, both. But when you add your covariates into a model, so you're estimating a conditional effect. The interpretation of your regression coefficient is different, because you say the effect of vaccination controlling for the effect of age. Okay, so that will be interpretation of your regression coefficient. But you might misspecify your model, because you see, I know my model, so that's why I have been able to correctly specify the correctly estimate this negative 0.2 value. But typically this model is not known. It may be a different link function if you're talking about logistic regression. It can be a different form for the covariate. So it's just different approach. It's just different approach. It just accidentally, in my example, you're talking about the same value. Okay.
Yeah, thanks.
Mm-hmm. Any other questions?
Hi, it's Mike Putman here. I just had a question. Is there what are your thoughts on just propensity matching versus inverse propensity weighting? Do you think it's preferable to do propensity weighting because you can keep more people in your sample? Just general thoughts about the different types of matching that one could do.
Why would you do matching? Okay, typically you do matching if you want to collect some additional information, right? For example, if you go into Trinetics, you identified your cases, but you want to do like blood tests, right? Or you want to do like chart review. So in this case, you are collecting this additional information. So in this case, matched pair would be a good design to proceed because additional information needs to be involved. But overall, if you just want to evaluate, population level effect of a rare disease on an outcome, I would proceed with a cohort study. I would just, extract all data and proceed with a cohort study. Propensity scores are, just useful way to balance two groups. Okay. And you see distribution of covariates. For example, suppose you're talking about a rare disease, which is mostly attributed to older people, okay? So in this case, if you do propensity score matching, you will also select controls from an older population. So your population you make an inference about will be different from overall population of patients. It depends what kind of inference you want to do. And this at-risk population, how would you describe it? So you don't have, exact sharp inclusion criteria. So that's a limitation of this propensity score matching. But again, sometimes it's really useful because you are focusing on this specific population at risk.
And then, sorry, one follow-up question using inverse propensity weighting. So, when you did it here, you inserted the weights into the weight function of your GLM, right?
Yes.
Can you do the same thing in R just using a Cox proportional hazards model, or is it more complicated?
Yes, I think you can do it.
Okay, because that's what I'm doing that right now, but it's been a little wonky. All right, thank you.
Yeah, I think you can do it. You're just balancing out, population of.
So this might be silly, but if you have, I haven't really considered using propensity weight scores or whatever for so many purposes. We use it kind of to look at outcomes where we have maybe a bias loss to follow up, try to adjust for that, but that's the only time we've really used it. If you have like say 3 covariates and you use them to develop propensity scores versus add them to your model as covariates, will that main effect of interest come out the same or different depending on, you know what I mean?
Yes, and sometimes it's different, sometimes it's the same. It depends on the situation. So, but what I saw, because that will be interpretation-wise, it's different because you are balancing your population and you have approximately the same distribution. After reweighting, you have approximately the same distribution in the intervention and in the control group. So that's why it's a hypothetical scenario, okay? If you are just applying regression modeling, it's not causal inference. You just evaluating the impact of a covariate controlling for other factors, okay? So that's a different scenario. It's not a hypothetical scenario. And what I saw people do sometimes, they, in addition to reweighting, they also apply additional control variables. So it's just a slightly different scenario. You're modeling not a real scenario, but a hypothetical scenario. If you would just run a regression model, that will be adjusted effect. But you keep in mind that in control group, you have younger folks, and intervention group, you have older guys, right? So this is what you're estimating. But if you did reweighting, in this case, you have approximately the same distribution of ages in between two groups. And you also control for effect of other variables. So potentially you can get different values, different quantities.
Sure. Thanks.
And I see an email. Okay, thank you. All right, thank you very much. Enjoy your.
This is recorded. Is this recording available? I would love to have a couple of my students watch it.
Okay. Yeah, I think so. And let me stop recording now. So where is it? Yeah. I will stop sharing first. New share. Stop share. Okay. And then I stop recording.